Hello everyone, I am here to explain NFA to DFA conversion with some examples. Let us know the contents. Introduction, steps to convert NFA to DFA conversion and examples of NFA to DFA conversion. At last is conclusion. Firstly, introduction about the DFA. DFA that refers to the deterministic finite automaton. A finite automata is said to be a deterministic if corresponding to an input symbol there is a single resultant state. There is only one transition between two states. A deterministic finite automata is a set of 5 tuples represented as m is equal to q summation transition q0 and f, where q is represented as a non-empty finite set of states in the finite control q0, q1, q2, and summation that a non-empty finite set of input symbols. Transition, it is a transition function that takes two arguments, a state and input symbol. It returns a single state. Q0 represents that it is a starting state, one of the states in Q. F that represents a non-empty set of final states or accepting the states from the set belonging to Q. Secondly, what is NFA? NFA refers to non-deterministic finite automata. A finite automata is said to be a non-deterministic if there is more than one possible transition from one state on the same input symbol. A non-deterministic finite automata is also a set of 5 tuples and represented as m as q summation transition q0 and f, where q represents a set of non-empty finite states and summation represents a set of non-empty finite input symbols. Transition that function that takes a state from q and an input symbol from and returns a subset of q. q0 that is initial state of NFA and member of q. F represents a non-finite set of final states and member of Q. Converting from NFA to DFA, the following steps are followed to convert a given NFA to a DFA. Step 1. Let Q dash be a new set of states of DFA and Q dash be a null in the starting. Let T dash be a new transition table of a DFA, and in the step 2 add start state of the NFA to the Q dash. Add transition of the start state to the transition table T dash. Its start state makes transition to a multiple states for some input alphabet, then treat them as a multiple states as a single state in DFA. In the step 3, if any new state is present in the transition table, add the new state in the Q dash. Add the transition of the state in the transition table T dash. Step 4. Keep repeating step 3 until no new state is present in the transition table. Finally, the transition table T dash so obtained is the complete transition table of the required DFA. The practice problems that is based on converting from NFA to the DFA. Problem 1, that convert the following non-deterministic finite automata NFA to the deterministic finite automata. In this example, we can see that there are three states Q0, Q1 and Q2. In the Q0, we have the transition A, B to the Q0, and Q0 to the Q1, we have transition element as B. From Q1 to the Q2, we have the transition element B, and thus the Q2 is a final state. Let us know the solution. Let Q dash be a new set of states of deterministic finite automata. In this table, we can see state transition elements, that is A and B. The start state is Q0. Q0 on A is Q0 only, and Q0 on B is, it consists of Q0 and even the Q1, because it's an NFA, that is it consists of multiple transition between two states. And Q1 on A is there is no states, and Q1 on B is only the Q2. Next is Q2 on A is also no transition, and Q2 on B is also there is no transition. Step 1, that is, let Q dash be a new set of states of deterministic finite automata. Let T dash be a new transition table of the DFA. Add the transitions of start state Q0 to the transition table T dash. Step 2, add the transitions of the start state Q0 to the transition table T dash. In the step 3, we get the new state present in the state Q dash is Q0 and Q1. Add the transitions for the set of states Q0 and Q1 to the transition table T dash. Therefore, we add the Q0 and Q1 to the Q dash, thus Q0 and Q1 on A is only the Q0, and Q0 on and Q1 on the B is Q0, Q1 and Q2. In the step 4, new state present in the state Q dash is Q0, Q1 and Q2. Add the transitions for the set of states Q0, Q1 and Q2 to the transition table T dash. In this table, we have added the Q0, Q1, Q2 in the state or the alphabet. Now, let us note Q0, Q1, Q2 on the A is only the Q0, and Q0, Q1, Q2 on the B is Q0, Q1 and Q2. In the step 5, since no new states are left to be added in the transition table T dash, so we stop. States containing Q2 as its component are treated as the final states of the DFA. Finally, transition table for the deterministic finite automata. Finally, we obtain this table by adding the new state to the transition table T naught. By using this table, the deterministic finite automata may be drawn as in the Q naught on A is only the Q naught, and Q naught on B is Q naught Q1, and next is Q naught on A is the Q naught, therefore it written as backwards to the Q naught, and Q naught Q1 on B is Q naught Q1 Q2. And finally, considering the Q0, Q1, Q2 on A is Q0, and Q0, Q1, Q2, and on the B is same state. Therefore, in the presence of Q2, therefore we made it as final state. This is the obtained final deterministic finite automata. Conclusion: adding the non-determinism capability to the DFS does not result in any new capability to accepting the languages. The set of languages that can be accepted by a NFA is exactly the same set of languages that can be accepted by a DFA. We proved this constructively. Every DFA is automatically an NFA without non-determinism. So, DFAs obviously cannot accept the languages that NFAs cannot. And any NFA can be converted using an algorithm to a DFA. So, NFS cannot accept the languages that DFS cannot. Thank you, everyone.